Welcome to Module 2, Pervasive Attack Surfaces and Control, part of the CompTIA Security Plus Guide to Network Security Fundamentals. Today we'll dive into the fundamental concepts of attack surfaces and the controls necessary to mitigate these threats. This session is crucial for anyone looking to strengthen their understanding of network security. By the end of this module, you should be able to define social engineering and list types of attacks. You'll gain a comprehensive understanding of social engineering, the deceptive practice of manipulating individuals into divulging confidential information. We will explore various types of social engineering attacks, including phishing, pretexting, baiting, and tailgating. These examples will help you recognize and anticipate potential threats in real-world scenarios. List different types of physical defenses. Physical security is a critical aspect of information systems security. You will learn about various physical defenses designed to protect your organization's assets. These include access control measures such as locks, security guards, surveillance cameras, and biometric systems. By understanding these defenses, you'll be better equipped to secure the physical infrastructure of your systems. Describe controls for protecting data. Protecting data is at the heart of cybersecurity. In this module, you will explore different types of controls used to safeguard sensitive information. We will cover administrative controls like policies and procedures, technical controls such as encryption and firewalls, and physical controls that restrict physical access to data storage locations. These controls collectively ensure the confidentiality, integrity, and availability of your data. Through this module, you'll build a solid foundation in social engineering awareness, physical security measures, and data protection strategies, all essential for maintaining robust information system security. Social engineering attacks are sophisticated tactics used to elicit information or convince a user to take actions that compromise security. These attacks are almost always carried out through deception and manipulation, exploiting human psychology rather than technical vulnerabilities. Attackers may pose as trustworthy figures or create plausible scenarios to trick users into divulging confidential information, clicking on malicious links, or performing actions that can lead to security breaches. Social engineering relies heavily on human vectors as the attack surface, targeting the natural tendency of individuals to trust and respond to social cues, making it a powerful and dangerous method of attack. Social engineering relies heavily on human psychology, exploiting the natural tendencies and behaviors of individuals to gain unauthorized access to information or systems. Attackers use a variety of techniques to gain trust and manipulate their targets. Provide a reason. Attackers often offer a plausible reason for their request, making it seem logical and necessary. For example, they might pose as IT support needing access to a user's account to resolve an urgent issue. Project confidence. Confidence is key in social engineering attacks. Attackers project authority and certainty, which can make their requests seem legitimate and less likely to be questioned. They may impersonate high-ranking officials or experts to leverage this confidence. Use evasion and diversion. To avoid suspicion, attackers might use evasive tactics or divert attention away from their true intentions. They could create a sense of urgency or distract the target with unrelated tasks, ensuring their real motives remain hidden. Make them laugh. Humor can be a powerful tool in building rapport and lowering a target's defenses. By making the target laugh, attackers create a sense of camaraderie and trust, making it easier to manipulate them into revealing information or performing actions. These techniques, rooted in an understanding of human psychology, enable attackers to effectively manipulate their targets, making social engineering a potent and dangerous method of attack. Phishing is a common and dangerous cyber attack where an attacker sends an email message or displays a web announcement that falsely claims to be from a legitimate source, attempting to trick the user into taking an action. Variations on phishing attacks include spear phishing, targeted phishing aimed at a specific individual or organization, often using personalized information to make the attack more convincing. Whaling, a form of spear phishing targeting high-profile individuals such as executives or senior managers. Vishing, voice phishing, where attackers use phone calls to trick victims into divulging sensitive information. Smishing, SMS phishing, involving fraudulent text messages that lure recipients into providing personal information or clicking on malicious links. A type of phishing attack is a business email compromise, BEC, which exploits electronically making payments or transferring funds. Requests for funds appear to come from a legitimate source, making BEC a significant threat to organizations. Phishing is one of the largest and most consequential cyber threats facing both enterprises and consumers. Social engineering impersonation involves masquerading as a real or fictitious character and then playing out the role of that person to manipulate a target. One type of impersonation is brand impersonation, where a threat actor pretends to represent a well-known brand to build immediate recognition and trust. Redirection occurs when an attacker directs a user to a fake lookalike site filled with ads, for which the attacker receives money for traffic generated to the site. Two types of redirection are typo squatting, using misspelled versions of popular website URLs to trick users into visiting malicious sites. Farming, redirecting users from legitimate websites to fraudulent ones without their knowledge. Misinformation is false or inaccurate information spread without malicious intent, while disinformation is false information spread with malicious intent. An example of cyber disinformation is a hoax or a false warning intended to deceive or mislead. A watering hole attack targets a specific group of individuals, such as major executives working for a manufacturing company, who tend to visit a common website that an attacker infects with malware. Other methods by which threat actors gather valuable information include dumpster diving, digging through trash receptacles to find useful information; Google dorking, using advanced Google search techniques to locate information that victims have inadvertently posted online; shoulder surfing, observing someone entering secret information, such as a password or PIN, without drawing attention to themselves. These techniques highlight the diverse and sophisticated nature of social engineering attacks, underscoring the importance of awareness and vigilance in protecting against such threats. Which of the following is not a personal technique used by social engineering attackers to gain the trust of the victim? A. Provide a reason. B. Project confidence. C. Demand compliance. D. Use evasion and diversion. The correct answer to the question is C. Demand compliance. Social engineering attacks typically rely on the attacker's ability to gain the victim's trust through subtle manipulation and psychological techniques. These methods often involve A. Provide a reason, giving a plausible explanation for why a request or action is necessary, making it appear legitimate and reasonable. B. Project confidence, using a confident demeanor to engender trust, making the victim more likely to believe that the attacker is credible and has the authority to make the request. D. Use evasion and diversion, employing tactics that distract or mislead the victim, diverting their attention from the attacker's true intentions, and thereby easing the process of manipulation. In contrast, C. Demand compliance does not fit into the typical modus operandi of gaining trust through subtlety and manipulation. Demanding compliance is a direct and forceful approach that typically does not build trust. Instead, it may arouse suspicion or resistance from the victim because it lacks the nuanced approach of typical social engineering strategies that are designed to be more deceitful and seductive. This approach is counterproductive to gaining trust, making it the correct answer as it is not a technique used by social engineers to build trust with their victims. Industrial camouflage is a strategic approach employed by some organizations to enhance physical security by making their buildings appear nondescript or unremarkable. The objective is to avoid drawing attention to the facilities that might be targets for theft, espionage, or attacks. This technique helps in minimizing the perceived value or importance of a site to potential intruders, effectively reducing the risk of targeted actions. In conjunction with industrial camouflage, perimeter defenses are essential for securing the physical boundaries of a property. These defenses are designed to restrict access to unauthorized individuals and play a critical role in the overall security architecture of a facility. The components of perimeter defense often include barriers. Physical barriers such as fences, walls, and gates serve as the first line of defense, deterring unauthorized entry and defining the perimeter of the secure area. Security guards. Human presence is one of the most effective deterrents against intrusion. Security guards not only perform surveillance and monitoring duties but also respond to security breaches and assess the behavior of individuals near the perimeter. Sensors. These include a range of devices like motion detectors, infrared sensors, and vibration sensors that alert security personnel to any unauthorized attempts to breach the perimeter. Security buffers. These are additional layers of space around the core protected area, which can include controlled landscaping, vehicle barriers, or secondary enclosures that provide extra time to respond to an intrusion before the intruder reaches sensitive areas. Locks. Strong, tamper-resistant locks on all access points reinforce barriers and control entry, adding an additional layer of security. Together, these elements create a comprehensive defense system that protects an organization's physical assets from external threats. By combining subtle design elements such as industrial camouflage with robust physical security measures like perimeter defenses, organizations can significantly enhance their security posture and reduce the likelihood of successful attacks. To prevent the leakage of important data, physical security measures must address potential vulnerabilities in data transmission and storage. Two effective physical controls for this purpose are the use of Faraday cages and protected cable distribution systems. Faraday cage. A Faraday cage is an enclosure used to block electromagnetic fields. It is typically constructed using a conductive material mesh or continuous covering. By enclosing electronic devices or entire rooms within a Faraday cage, electromagnetic signals, including wireless data transmissions, are prevented from entering or exiting the enclosure. This is crucial for securing environments where sensitive information is processed or stored, as it protects against electronic eavesdropping and remote hacking attempts via radio frequencies. Protected cable distribution systems. These systems are designed to safeguard the physical integrity and security of wired data transmissions. Protected cable distribution involves using conduits, armored cable, or dedicated cable pathways that are resistant to tampering and interception. Ensuring that the cables carrying sensitive data are not exposed or accessible is vital to prevent data interception or damage. This can include implementing physical barriers around cables, using locks and surveillance on cable access points, and employing alarms to detect unauthorized access. Both of these controls are crucial in environments where the risk of data leakage could have significant ramifications, such as in government facilities, financial institutions, and research labs. Implementing these measures helps ensure that critical information remains secure and is only accessible to authorized personnel. Electronic devices, during their normal operation, emit electromagnetic fields which can lead to electromagnetic interference, EMI. This phenomenon not only affects the functioning of nearby sensitive devices but also poses a security risk because these emissions can be intercepted and decoded by unauthorized persons. This kind of data leakage is particularly concerning in secure environments where sensitive information is handled. To combat this, a Faraday cage, which is a metallic enclosure, plays a crucial role. It works on the principle of blocking electromagnetic fields. The structure of a Faraday cage, made from conductive materials, distributes electromagnetic charges or fields around the outside of the enclosure, thereby blocking them from entering or escaping the interior space. This effectively isolates devices inside the cage from external electric fields and also prevents internal emissions from being detectable outside the enclosure. For mobile or portable electronic devices, lightweight and portable Faraday bags are a practical solution. These bags are made from materials that mimic a Faraday cage's properties but in a flexible, portable form. Users can place devices such as smartphones, tablets, or laptops inside these bags to shield them from incoming or outgoing signals. This makes Faraday bags an essential tool for securing devices during transportation or in potentially insecure environments, preventing unauthorized access to electronic data via electromagnetic eavesdropping. A protected distribution system, PDS, plays a crucial role in safeguarding the transmission of classified information between secure areas. This system ensures that sensitive data remains confidential and is protected from interception or tampering during its transit through potentially vulnerable pathways. There are two primary types of PDSs that are commonly used to achieve this level of security. Hardened carrier PDS. This type of system involves the use of data cables that are installed within a conduit made from special electrical metallic tubing, EMT. The EMT is designed to be robust and resistant to physical breaches, effectively protecting the cables from being accessed or damaged. The hardened nature of the conduit serves as a physical barrier, deterring unauthorized access and providing a durable layer of protection around the critical data transmission lines. Alarmed carrier PDS. In this setup, the PDS includes specialized optical fibers within the conduit that serve a dual function. These fibers not only carry data but are also sensitive to acoustic vibrations. If an intruder attempts to access or tamper with the cables, these vibrations are detected by the optical fibers, which then trigger an alarm system. This immediate response mechanism helps to alert security personnel to potential breaches, allowing for rapid reaction to protect the integrity of the classified information. Both types of PDSs provide robust security measures for the transmission of sensitive data, each leveraging different strategies: physical durability in hardened carriers, and technological surveillance in alarmed carriers, to mitigate the risks of data leakage or tampering. The choice between a hardened carrier and an alarmed carrier PDS can depend on the specific security needs, threat assessment, and environmental conditions of the installation site. Knowledge check. Which type of sensor is most appropriate for monitoring a large warehouse for intruders? A. Microwave sensor. B. IR sensor. C. XG sensor. D. Passive RGP sensor. The correct answer is a microwave sensor. Explanation. Microwave sensors are particularly suitable for monitoring large areas such as warehouses for several reasons. Coverage area. Microwave sensors can cover large areas effectively. They emit microwave signals that can penetrate through various materials, allowing them to monitor extensive spaces without being obstructed by walls, shelves, or other structures commonly found in warehouses. Detection capabilities. These sensors can detect motion over a wide range and at a significant distance. This makes them ideal for large, open spaces where a single sensor needs to cover a broad area. Intruder detection. Microwave sensors are highly effective at detecting intruders because they can sense even small movements. They work by sending out microwave pulses and measuring the reflection of these waves. Any disturbance in the reflected signal indicates the presence of a moving object, triggering an alert. In contrast, other sensor types may have limitations that make them less suitable for large areas. IR sensors, infrared sensors. While effective for detecting heat signatures, IR sensors generally have a more limited range and may be obstructed by physical barriers within a warehouse. XG sensors. This option is not commonly known or used in the context of intruder detection systems. It might be a distractor in the question. Passive RGP sensors. This type is not standard in intruder detection and likely serves as a distractor in the question. Therefore, microwave sensors are the most appropriate choice for monitoring large warehouses due to their ability to cover wide areas and detect intruders effectively. Protecting data is essential for maintaining the confidentiality, integrity, and availability of information within an organization. Adequate controls must be implemented to ensure data security, involving several key aspects. Data classifications and types. Understanding the various classifications and types of data is fundamental. Data can be categorized based on its sensitivity and value, such as public, internal, confidential, and highly confidential. Each classification requires different levels of protection based on the potential impact of a breach. Types of data include personally identifiable information, PI, financial data, intellectual property, and operational data, among others. Consequences of a data breach. Recognizing the potential consequences of a data breach is crucial for motivating and guiding the implementation of security controls. Consequences can include financial loss, legal penalties, damage to reputation, loss of customer trust, and operational disruption. Understanding these impacts helps prioritize the protection of the most sensitive and valuable data. Controls for protecting data. Various controls can be put in place to safeguard data effectively. These include access controls, ensuring that only authorized personnel have access to sensitive data. This can involve the use of strong passwords, multi-factor authentication, and role-based access controls. Encryption, encrypting data both in transit and at rest to protect it from unauthorized access and interception. Data masking, masking sensitive data in non-production environments to prevent exposure during testing and development. Backup and recovery, regularly backing up data and having robust recovery processes in place to ensure data can be restored in case of loss or corruption. Monitoring and auditing, continuously monitoring access to and usage of data to detect and respond to suspicious activities. Regular auditing helps ensure compliance with data protection policies. Physical controls, implementing physical security measures such as secured facilities, access controls, and surveillance to protect data from physical threats. By understanding the classifications and types of data, being aware of the potential consequences of data breaches, and implementing appropriate controls, organizations can significantly enhance their data protection efforts and mitigate the risks associated with data breaches. Protecting data requires categorizing it by type and applying appropriate handling measures based on its sensitivity and potential impact if compromised. Here is a detailed description of different data types and their recommended handling procedures. Confidential data. Given its high sensitivity, access to confidential data should be strictly controlled. Only individuals with the highest level of authentication, typically involving multiple factors such as passwords, biometric verification, etc., should be granted access. Private data. This data should be accessible only to users who need to know the information to perform their job functions. Access controls should be implemented to ensure that only authorized personnel can view or use this data. Sensitive data. Sensitive data, which can cause significant harm if disclosed, should be highly restricted. Only employees with a clear business need and explicit approval should be able to access this information. Measures such as encryption, strict access controls, and monitoring should be in place. Critical data. The availability of critical data is crucial for the organization's operations. Protecting this data involves ensuring it is always available and secure. This includes regular backups, robust disaster recovery plans, and stringent security measures to prevent unauthorized access or loss. Public data. Since there is no risk associated with the release of public data, it can be freely shared and accessed by anyone. Public data does not require special handling but should still be accurate and reliable. Restricted data. This data type is not meant for public access and should be handled with care, especially when communicated via emails or other potentially insecure channels. Proper security measures, such as encryption and secure email protocols, should be used to ensure restricted data remains protected. By following these recommended handling procedures, organizations can ensure that each type of data is appropriately protected based on its sensitivity and potential impact. Protecting data involves understanding its various types and implementing the necessary controls to ensure its security. Here is a detailed description of different data types, along with explanations. Regulated data. This type of data is subject to external regulations that dictate who can see and use it and under what circumstances. Compliance with these regulations is crucial to avoid legal repercussions. Examples include data governed by HIPAA, Health Insurance Portability and Accountability Act, for health information, GDPR, General Data Protection Regulation, for personal data in the European Union, and PCI-DSS, Payment Card Industry Data Security Standard, for payment information. Intellectual property, IP, data. This data represents inventions or works resulting from creativity, such as patents, copyrights, and trademarks. Protecting IP data is vital to maintain competitive advantage and safeguard the rights of the creators. Trade secret data. This enterprise data remains undisclosed and provides a competitive edge, such as formulas, processes, designs, or business strategies. The confidentiality of trade secrets is essential for preserving the unique value they offer to the enterprise. Legal information. This encompasses general factual information about the law and the legal process. It includes documents such as statutes, case law, legal opinions, and court records. While some legal information might be public, sensitive legal strategies or case details require protection. Financial information. This includes data about the monetary transactions of the enterprise, such as revenue, expenses, profits, losses, and other financial metrics. Protecting financial information is crucial to prevent fraud, maintain investor confidence, and comply with financial regulations. Human-readable data. Data that a person can read and interpret without the need for special tools. Examples include text files, printed documents, and readable spreadsheets. This data is straightforward to access and understand. Non-human readable data, machine-readable data. Data that a device can interpret but is not readily understood by a person in its native state. Examples include JSON, JavaScript Object Notation, XML, Extensible Markup Language, and binary files. These data formats require specific software or systems to be interpreted and used effectively. Example of non-human readable data. JSON. JavaScript Object Notation is a lightweight data interchange format that is easy for machines to parse and generate. It is commonly used for transmitting data between a server and a web application. Understanding these data types and their specific requirements for protection is crucial for developing comprehensive data security strategies that align with both internal needs and external regulatory requirements. When an organization suffers a data breach, it can face numerous severe consequences. Here are some of the potential impacts. Reputation damage. A data breach can significantly tarnish an organization's reputation. Loss of customer trust, negative media coverage, and the perception of weak security practices can lead to a decrease in customer loyalty and a potential loss of business. Restoring a damaged reputation can take considerable time and effort. Intellectual property, IP, theft. Breaches involving the theft of intellectual property can have long-lasting repercussions. Stolen IP, such as proprietary technologies, trade secrets, and confidential business strategies, can be used by competitors to gain an unfair advantage or by malicious actors to undermine the organization's market position. Fines. Regulatory bodies often impose hefty fines on organizations that fail to protect sensitive data, particularly if they are found to be non-compliant with data protection regulations such as the General Data Protection Regulation, GDPR, in the EU or the Health Insurance Portability and Accountability Act, HIPAA, in the US. These fines can be substantial and have a significant financial impact on the organization. Legal action. Victims of the data breach, including customers, partners, or employees, may file lawsuits against the organization for failing to protect their personal information. Legal battles can be costly and time-consuming, potentially leading to additional financial penalties and settlements. Operational disruption. Data breaches can disrupt normal business operations. Systems may need to be taken offline to address the breach, investigate the incident, and implement corrective measures. This disruption can result in lost productivity and revenue. Financial loss. Beyond fines and legal costs, an organization may face direct financial losses from the theft of sensitive financial information, fraudulent transactions, and the costs associated with mitigating the breach, such as incident response, notification to affected individuals, and investment in enhanced security measures. Customer attrition. Following a breach, customers may choose to take their business elsewhere, fearing for the security of their personal information. The loss of customers can lead to a decline in sales and market share. Increased scrutiny. Post-breach, an organization may face increased scrutiny from regulators, investors, and the public. This heightened attention can lead to more stringent regulatory requirements and a greater emphasis on demonstrating robust security practices. In summary, the consequences of a data breach extend far beyond immediate financial costs. They encompass damage to reputation, loss of intellectual property, regulatory fines, legal ramifications, operational disruption, and long-term financial impacts. Organizations must take comprehensive measures to prevent data breaches and mitigate their potential consequences. When creating data controls, several general considerations about data must be taken into account to ensure effective protection. Here are the key points to consider. Data state. Understanding the state of the data is crucial, as different states require different security measures. Data can reside in one of the following three states. Data in processing. This is data actively being used or processed by applications. It requires protection against unauthorized access and tampering during the processing phase. Data in transit. This is data that is being transferred between locations, such as across networks or between devices. Encryption and secure transmission protocols are essential to protect data in transit from interception and unauthorized access. Data at rest. This is data that is stored on physical or virtual storage media. Security measures such as encryption, access controls, and physical security are important to protect data at rest from unauthorized access and breaches. Data location. Knowing where the data is physically located is important for applying appropriate controls and complying with legal requirements. Geolocation. This encompasses all techniques that identify the data's physical or logical location. Understanding geolocation helps in applying specific security measures and in complying with regional regulations. Data sovereignty. This refers to the country-specific requirements that apply to data, based on where it is collected, processed, or stored. Data is subject to the laws and regulations of the country in which it resides, which can affect how it must be handled and protected. For instance, some countries have strict data localization laws requiring that data be stored within their borders. When developing data controls, it is essential to consider the state of the data, whether it is in processing, in transit, or at rest, and to apply appropriate security measures for each state. Additionally, understanding the data's location through geolocation techniques and complying with data sovereignty laws is crucial for legal compliance and ensuring robust data protection. By addressing these considerations, organizations can create effective data controls that safeguard information across its entire lifecycle. To enhance the protection of data, organizations can implement a variety of techniques. Each technique offers unique benefits in securing sensitive information. Here are some key techniques. Data minimization. This technique involves collecting and retaining only the data that is necessary for a specific purpose. By reducing the amount of data collected and stored, organizations can minimize the risk of data breaches and ensure compliance with data protection regulations. This approach limits exposure to potential threats and decreases the attack surface. Data masking. Data masking protects sensitive information by replacing it with fictitious but realistic data. This process ensures that data used in non-production environments, such as for testing or training, does not expose real sensitive information. Masked data retains its format and usability, making it safe for use in scenarios where real data is not required. Tokenization. Tokenization replaces sensitive data with unique identification symbols, tokens, that retain essential information without compromising security. The actual data is stored securely in a separate location called a token vault. This technique is especially useful for protecting payment card information and other personal identifiers, as tokens can be used in transactions without exposing the original data. Restrictions. Implementing strict access controls and permissions ensures that only authorized personnel can access sensitive data. This includes the use of role-based access control, RBAC, multi-factor authentication, MFA, and the principle of least privilege, POLP, which grants users the minimum level of access necessary to perform their job functions. Regular audits and monitoring can help maintain and enforce these restrictions. Segmentation. Data segmentation involves dividing the network into smaller, isolated segments to limit the spread of an attack. This technique helps contain potential breaches and reduces the risk of unauthorized access to sensitive data. Network segmentation can be achieved through firewalls, virtual LANs, VLANs, and other isolation methods. Additionally, data can be segmented based on its sensitivity level, ensuring that more sensitive data receives higher levels of protection. By implementing these techniques, organizations can significantly enhance their data protection strategies, reducing the risk of data breaches and ensuring compliance with data protection regulations. Knowledge check. Which data classification has the highest level of data sensitivity? A. Eyes only. B. Sensitive. C. Private. D. Confidential. The correct answer is D. Confidential. Here is why. Confidential data classification typically denotes information that requires the highest level of protection due to its sensitive nature. This data is often restricted to a very limited number of individuals who have been specifically authorized to access it. The following points clarify why confidential is considered the highest level of data sensitivity. Access restrictions. Confidential data is only accessible to users with the highest level of pre-approved authentication. This means stringent access controls are in place to ensure that only individuals with a legitimate need and proper authorization can view or handle this data. Potential impact of breach. The unauthorized disclosure of confidential data can result in severe consequences, such as significant financial loss, legal penalties, and irreparable damage to an organization's reputation. Therefore, it demands the most robust security measures. Examples of confidential data. This category often includes highly sensitive information like trade secrets, proprietary business information, classified government data, and other critical business assets. The loss or compromise of such data can have catastrophic implications. Let's compare relative to other classifications. Eyes only. While this term implies restricted access, it is not as commonly used in standard data classification frameworks as confidential. Sensitive. This data classification is important and requires protection but is typically one level below confidential in terms of sensitivity. Private. This classification pertains to personal information that needs protection but is not as critical as confidential data in terms of potential impact. Given these points, confidential is recognized as having the highest level of data sensitivity among the given options, justifying the answer choice and explanation. Self-assessment. Rate your competence of the following module objectives on a scale of 1 to 5, where 5 indicates you have full confidence in your competence of that objective and 1 indicates you have very little confidence in your competence of that objective. If you self-score less than 4, you should consider reviewing the module and related exercises. 1. Define social engineering and list types of attacks. 2. List different types of physical defenses. 3. Describe controls for protecting data. Thank you for joining us in this lesson on social engineering and data protection. Here's a quick recap. Social engineering attacks. We discussed how social engineering deceives individuals into compromising security, including phishing and impersonation. Physical defenses. We covered security measures like industrial camouflage, perimeter defenses, Faraday cages, and protected distribution systems. Data protection controls. We talked about data minimization, masking, tokenization, restrictions, and segmentation to secure data in different states. If you found this video helpful, please like, subscribe, and share. Your support helps us create more valuable content. Thanks for watching, and see you in the next lesson.